there is something deeply wrong with the universe. Not wrong in a philosophical sense, wrong in a measurable, mathematical, impossible to ignore sense. When scientists look at the most detailed images of deep space ever captured, images containing nearly 800,000 galaxies, they run the numbers. They add up all the visible matter, every star, every gas cloud, every glowing filament of light, and when they are done, the total comes up short, catastrophically short. There isn't enough gravity in any of it to hold those galaxies together. By every calculation we have, those galaxies should be flying apart right now. The fact that they aren't means something invisible is doing the work, something we have never directly seen, never touched, and never caught in a single laboratory instrument. We gave it a name, dark matter, mostly because we needed to call it something. But for decades, naming it was about the limit of what we could do. That changed in early 2026. Using the James Webb Space Telescope, a team of researchers mapped something that has never been mapped before at this resolution. Not the galaxies, not the stars. The invisible structure underneath all of it, the skeleton the universe is built on. And what they found didn't just confirm what we suspected, it quietly broke something in our best theory of how the cosmos works. A discrepancy so precise, so consistent across hundreds of thousands of data points, that physicists are now being forced to ask a question nobody was expecting to ask this soon. What if our model of the universe is incomplete? We'll get there. But first, you need to understand what was actually built here, and why it took this long. The idea that something invisible was holding galaxies together isn't new. Fritz Zwicky proposed it in 1933 after noticing that galaxies inside the Coma cluster were moving far too fast. The visible matter couldn't explain it. The math didn't work. He suggested there was mass we couldn't see, and the physics community largely ignored him for 40 years. Then came Vera Rubin. In the 1970s, Rubin was measuring how stars move inside spiral galaxies. The expectation, based on Newtonian gravity, was straightforward. Stars near the center of a galaxy orbit fast because they're close to the bulk of the mass. Stars near the outer edges orbit slowly because they're far from it. The same way the outer planets in our solar system move more slowly than the inner ones. Rubin found the opposite. Stars at the far edges of galaxies were orbiting just as fast as the ones near the core. In some cases, faster. There was no explanation for this using visible matter alone. The only thing that fit the data was a vast invisible halo of mass surrounding every galaxy, extending far beyond its visible edges. You couldn't see it, you couldn't touch it, but it was clearly there, doing gravitational work on a scale that dwarfed everything we could observe. Cosmologists today estimate that dark matter makes up roughly 27% of the universe's total mass energy content. Everything we can see, every star, planet, nebula, and galaxy, adds up to about 5%. Let that land for a moment. The entire visible universe is a 5% rounding error on the real total. For decades we could feel dark matter's gravity pulling on things. We could track its influence the way you might track a large animal through a forest by watching which trees shake. But we couldn't see it directly. We had no map. We had rough guesses at where it concentrated. But the fine structure, the thin bridges, the filaments, the detailed architecture was completely invisible to us. That is what changed in 2026. And this is where the story starts to get uncomfortable. The technique that made this map possible is called weak gravitational lensing, and it works because of something Einstein showed us more than a century ago. Mass doesn't just attract other mass. Mass curves space itself. When light from a distant galaxy travels toward us, it doesn't always travel in a straight line. If there is a massive concentration of dark matter sitting between us and that galaxy, the light follows the curve of the space around that mass. It bends, slightly, almost imperceptibly, and when it arrives at our telescope, the image of that distant galaxy looks subtly distorted, stretched, smeared, elongated in a direction it shouldn't be. This is and the distortion it creates is so small you cannot see it by looking at one galaxy, or 10, or 1,000. The signal is buried in the natural variation of galaxy shapes. To pull it out of the noise, you need an enormous sample. You need to measure hundreds of thousands of galaxies, look at the statistical pattern of how their shapes are being pulled, and work backward to calculate the mass that caused it. Think of it like standing in a massive room and trying to figure out where the hidden magnets are by watching how hundreds of thousands of compass needles are being deflected. No single needle tells you much, but the pattern across all of them gives you a map. This is exactly what the Cosmos Web Survey did. The team focused on a specific patch of sky in the constellation Sextans, an area covering about 0.54 degrees, 2.5 times the size of a full moon. For a high-precision instrument like JWST, that is an enormous canvas. Most deep space observations are done through what amounts to a narrow straw. This survey was designed to be a continuous, unbroken map of a huge region with no gaps, no holes. A complete picture. The lead investigators, Jan Cartel and Caitlin Casey, designed this to be the largest program JWST has ever taken on. Hundreds of hours of observation time, nearly 800,000 individual galaxies identified, many of which had never been seen before. Too faint, too far, too red for older telescopes to pick up. And this is where the JWST changes everything. Older telescopes like Hubble were exceptional at capturing visible light. But the further you look into deep space, the older the light, and old light is stretched. It has shifted into infrared wavelengths, longer, redder, invisible to instruments not built for it. Hubble couldn't fully access those wavelengths. JWST's Aniarchum instrument was built specifically for them. It can see through cosmic dust that would otherwise block these background sources entirely. Without it, the background galaxies you need to measure the lensing effect simply vanish from view. The result was a source density of 129 galaxies per square arcminute, roughly twice anything achieved before. That number matters more than it might sound. At that density, researchers didn't just see isolated clumps of dark matter, they started seeing the threads connecting them. The difference between seeing a few scattered islands and finally seeing the ocean floor that links them all. What the map showed was not what anyone expected, or rather, it was what theory predicted in broad strokes, but at a detailed level that revealed something theory had quietly been getting wrong. For a long time, the mental model of dark matter was simple: giant invisible blobs, sitting at the centers of galaxy clusters, isolated, massive, spherical, like invisible boulders scattered across the void. The 2026 map is nothing like that. What it shows is a network, not a collection of separate objects, but a continuous web of filaments, long, thin bridges of invisible mass, stretching across hundreds of millions of light-years, connecting one galaxy cluster to the next. An architecture so vast it makes individual galaxies look like dewdrops on a spiderweb. These filaments are the real structure of the cosmos, and where the map shows the densest filaments, the data shows the highest concentrations of hydrogen gas, the most active star formation, the thickest clustering of galaxies. The regular matter, the stuff we can see, is following the dark matter, like water following grooves carved into stone. It isn't coincidence. The dark matter laid the grooves first. This is what cosmologists mean when they say dark matter was the original blueprint. In the earliest moments after the Big Bang, everything was almost perfectly uniform. Hydrogen spread nearly evenly across a rapidly expanding space. But dark matter, because it doesn't interact with light or heat, began collapsing under its own gravity first. Before regular matter could do anything, dark matter was already pulling itself into these long strands, creating deep gravitational wells, trenches in the fabric of space, and the hydrogen gas drifted in, slowly at first, then faster, compressing, heating, until, eventually it reached the density and temperature required to ignite nuclear fusion. The first stars were lit by gravity wells, carved by something invisible. Every star that ever burned, every heavy element ever forged, every planet that ever formed, all of it traces back to the architecture this map is showing us for the first time. When you look at those dark matter filaments, you are looking at the construction timeline of everything, including yourself. But here is where the data starts doing something unexpected. The lambda CDM model, lambda called dark matter, is the standard framework cosmologists use to describe the universe. It has been extraordinarily successful. It predicts how galaxies cluster, how the cosmic microwave background looks, how structures grow over billions of years. It is one of the best tested theories in all of science, and the 2026 map is quietly disagreeing with it. The specific tension is called sigma, is a measure of how clumpy the universe is, how tightly dark matter bunches together into dense structures at large scales. According to the lambda CDM model and the measurements of the early universe from the Planck satellite, the universe should be a certain level of clumpy, dense, sharp, well-defined filaments, Tight, concentrated clusters dot the cosmos web map, shows something measurably smoother.